All right, let's consider the shape of these molecules because this ends up being really impactful for overall physical and chemical properties. H2O, water, is a bent molecule, and this is because of the lone pairs on oxygen, which we'll discuss in a minute. CO2 is a linear molecule. It's got no lone pairs and therefore is linear in shape. And these are kind of comparable molecules, right? They're similar-ish in size. They've got one central atom with exterior atoms, but water is bent. Water's liquid at room temperature. Water's the solvent of life. CO2 is another important molecule, but it's not really the solvent of life. It's gaseous at room temperature. Things are very different physically between water and CO2. And this is very much to do with the shape of the molecule. How can we predict and understand why this is the case? So why is water bent, right? Let's look at the following depictions and remember that when we consider our pairs of electrons, of which there are covalent bonds, the sticks, or non-bonded electrons, two dots, it's still a pair of electrons. And electrons are negatively charged, and because they're negatively charged, they all want to push apart from each other and take up equal space around the oxygen. And so because of this, there are two lone pairs on oxygen, which are not shown on the left and shown on the right. What we can see on the right is that all of the different electrons, right, the lone pair electrons and the bonded electrons, this is 4 groups of electrons around the central purple atom, they all want to push away from each other and make for a structure where everyone kind of is pushing for as much room as they can. And because of that, the lone pair electrons push the bonded electrons away from one another and make a bent structure that looks like what is on the left. We don't really consider the electrons as the matter because remember, electrons are so much smaller than the atoms, right? An electron is less than 1,000th of the mass of even a hydrogen. And so they're not really a meaningful part of the physique of a molecule. However, they are a meaningful part in distorting that shape. Water looks like a bent structure that appears here. And if we look back at CO2, there is no lone pair on CO2, on the carbon of CO2, and therefore those two double bonds push each other apart and do so to complete opposite sides of the central atom. Again, water bent, CO2 linear. This makes for a wide variety of different properties, which we're going to discuss here. The most notable of these is polarity. And so when we look at an overall molecule, some molecules are what we call polar, where we have more electrons on one side than the other. And this comes from one of the atoms in the bonds that's taking more electrons than the other is. And HCl is a good example. When we have HCl, hydrogen does not pull the electrons as much as chlorine. Remember that a covalent bond is a shared pair of electrons. By pulling more of the electrons towards itself, chlorine makes negative charge on its side, leaving positive charge on hydrogen, and there's like an arrow that's almost like a magnet that shows this bond is polar. Electronegativity is a measure of how strongly an atom attracts those electrons, and in this case, chlorine is more electronegative than hydrogen. For the most part, we're not going to talk too much about electronegativity in this course, but note that this causes polarity, and this has a lot of implication biologically, whether a bond is polar, has a buildup of electrons on one side or the other, and it comes from this preference of atoms to hog the electrons that are within a bonded pair, and we call this electronegativity. If we are equal, right? So let's say we have two identical atoms in a bond, so two oxygens. Well, these both want the electrons exactly the same way, and in this case, we do not have any buildup of electrons on one side or another. We would say this is a non-polar covalent bond and does not behave like a magnet, right? Polar means one side is charged one thing, the other side is charged the other, and so this is non-polar where we don't have like a magnetism, so to speak, to the atom. Okay, the shape matters as well because when we have a polar covalent bond, these can, based on the shape, contribute to an overall polar molecule. So here, if we look at hydrogen and oxygen, oxygen's a little bit more electronegative. It's going to have a slight buildup of charge compared to the hydrogen. But note that the whole molecule is only going to have a net magnetism if these bonds make it so they add up to some sort of a total that's not zero, right? If it was like tug of war and they were pulling exactly opposite each other, like the case with CO2, it would end up being non-polar because it would all cancel out. But if we look here at water, we see that the bent structure means that when we have oxygen with a slightly negative charge, that's what these little lowercase deltas mean, and hydrogen with a slightly positive charge, we end up having something that has what we call a net dipole, and that's the bottom blue arrow, right? The orange arrows show the polarity of the individual bonds. The fact that there's an asymmetry means we have an overall net dipole, and this means that water is like a little magnet. And this is very significant because the nature of water being like a little magnet, having negatively charged and positively charged areas, well, this is why water dissolves ionic compounds so well. They're charged, and water has a charge-like nature that can kind of worm its way into the electric environment. Water is able to do this. Something that doesn't have a dipole would not. Looking at CO2, right? This is the reason why water and carbon dioxide are different. In carbon dioxide, it is true that we have dipoles between each carbon and oxygen, but remember it's a linear molecule. Because they're exactly the same difference, right? It's carbon and oxygen on both sides. We don't have any overall dipole. They cancel out on each side because it's linear. Water is bent, and therefore they do not completely cancel. We have this overall dipole. This is the reason why water is liquid at room temperature. It clings to itself and has many, many other properties that we're going to look at in the future videos.